Okay, so hi everyone. So welcome back to yet another video. So today in this video we will be discussing about this Leetcode hard problem. The name of the problem goes by minimum edge weight equilibrium queries in a tree. This problem will utilize the concept of mainly two things. The first one is the binary lifting in order to find the LCA between two nodes, and the second concept will be of DP on trees. So I'll tell you step by step how we will solve this problem. So the problem reads like this. There is an undirected tree with n nodes labeled from 0 to n minus 1, right? So we have a tree with n nodes and the nodes are labeled from 0 till n minus 1, and then you are given an integer n and a 2D integer array edges of length n minus 1, and each of the element of this 2D array consists of three integers, that is u, v and w. So what does these integers represent? So it represents that an edge is connecting the nodes u and v bidirectionally, and the weight of this edge is this w. And we are also given another 2D integer array queries of length m. Each query will hold two elements, that is a and b. So what are these a and b? So these a and b are just two nodes of this given tree, right? So for each of the query you have to find the minimum number of operations that is required in order to make the weight of every edge on the path from A to B equal. So in one operation you can choose any edge of the tree and change its weight to any value. So what we have to do is, for a given query between those two nodes, we have to make the edge weights equal for every edge on that path. And note that queries are independent of each other, meaning that the tree returns to its initial state on each new query. So we have to answer each query individually. They are not linked. And the path from A to B is a sequence of distinct nodes starting from A and ending at B, such that every two adjacent nodes in the sequence share an edge in the tree. And finally we have to return an array answer of length m, that is the same as the number of queries, where answer of I will be the answer to the ith query. So in the input we are given n, that is the total number of nodes, and then vector of int edges, which is the description of the tree consisting of three integers u, v and w, and then another 2D array queries which will consist of two integers each time, that is two nodes a and b, and we have to find the minimum number of operations such that every edge on the path from A to B becomes equal. So this is the question, and for this question we are initially given with two examples, as you can see. So we will discuss these two examples one by one in the blackboard, and we'll see how the outputs are coming for each one of them. So let us now go to the blackboard and understand the solution. So as you can see, this is the very first example of the question, and in this example we are given a total of 7 nodes, that is from 0 to 6, as you can see in this tree, and the expected output for this example is 0, 0, 1 and 3. That is 0 for the first query, second 0 for the second query, this third 1 for the third query, and this fourth 3 for the fourth query. So let us now see how for each query these outputs are coming. So as you can see that the very first query is between nodes 0 to 3. This is our 0th node and this is our third node. So this query is asking us to give the minimum number of operations that we will perform in order to make every edge weight present between these two nodes, that is on this path, equal. So let me mark these two nodes. So this is our 0th node and this is our third node, and we have to find the minimum number of operations to make every edge weight present between these two nodes on a path equal. So if you remember, the given graph is what? The given graph is a tree, right? So it means that the total number of edges will be equal to total number of nodes minus 1. As you can count here also that the total number of nodes is 7 actually, that is from 0 to 6. So it means that the total number of edges should be equal to 7 minus 1, that is 6. And it is true because this is the first edge, this is the second, this is the third, fourth, fifth and sixth. Each example will consist of a tree only, that is n vertices and n minus 1 edges, which is the definition of tree also. And if you know, then in a tree between any two nodes, then between those two nodes there will always be a unique path. Suppose I had a graph initially that looked something like this. Suppose this was a graph, and clearly this is not a tree, right? Because a cycle is getting formed, and in a tree there can be no cycles, right? So if this was a graph and we are asked to find a path between the source and the destination, then what answers could have been possible? So clearly there could have been two answers only. So this was our very first answer, that is this path, and this would be our second answer, that is this path. So why did that happen here? This happened because this was a graph and not a tree. So a cycle was getting formed here, right? Because of this cycle, that is this back edge connecting itself to here, another path was getting involved in the answer. So had been this edge was absent, so we could have said that there was actually one path only from the source to the destination. But because of this back edge only, that is this cycle, we got two different paths, right? So it should be clear to you by now that whenever we would be given with any cycle, then between any two pair of nodes, the path will always be unique. This is also a definition of the tree, right? So keep this in mind, that between any two pair of nodes in a tree, there will only be one path from that node to other node. So if you remember, then the first query was between 0 and 3, that is this node and this node. And in this we are asked to find the minimum number of operations to make the every edge weight along this path equal. So now you know that if we are asked to answer the query between these two nodes, then there will always be one path only. So we don't have to worry about multiple paths because this is a tree. So there will just be one path, and hence we have to minimize the number of operations for this path only, right? So now let's try to answer this query. So if you look, then between these two nodes, this is the path, right? And hence there are three edge weights. So if I write down the edge weights, then the edge weights are as follows. So the first one is 1, the second one is 1, and the third one is also 1. So as you can see that every edge weight present along this path is already equal. And if you remember, then what the question was asking us and demanding us, it wants us to make every edge weight on this path equal. But here it's already equal, that this one is equal to this one and this one is equal to this one. So every edge weight is already equal in this path. So it means that we don't have to manipulate or change any edge weight because things are already sorted. So we can say that for this query, since all edge weights are equal, so we don't have to perform any operations. So no operations should be performed, and hence we can say since no operations are required, that is zero number of operations. So that's why for this first query the output is 0. So I hope you understood the very first query, right? So it was an easy one, right? So now let's go and check out the second query of this example. So this is our second query. So the first node is 3 and the second is 6. So I have marked this here. So this is our 3 and this is our 6. So again, if we try to answer the query, that is to find the minimum number of operations to make every edge weight on the path from this node to this node equal, that is along this path, then it is clearly visible that already every edge weight is equal to 2. So 2, 2, 2 along this path. So again, we can say that we don't have to perform any operations because things are already sorted, and that's why we can say the total number of operations again required to make this query possible is 0 only, right? So that's why for the second query, the answer is again 0. Now we are done with the second query. Let's check out the third query now, that is 2 and 6. So I have marked the nodes here now, that is 2 and this 6. Now things will start become interesting. So these are our nodes now, and this is the unique path between them. So it means that now what we have to do is, along this path, we have to make every edge weight equal. So as of now, what is the condition? So the edge weights in this case are 1, 2, 2 and 2, right? This 1 and then 2 and then again 2 and then again 2. So we want every edge weight of this path to be equal. And if you have read the question, then it is clearly written that we can choose any edge of the tree and change its value to any value. So we have the liberty to pick up any edge and change its weight to any value. So now if you see, this is 1 and these are the 2's, right? So I can pick this one and change it to any value, whatever I want. Similarly, I can pick this and change it to any value. Similarly, I can pick this two and change it to any value, and same for this two. I can change it to any value. But since the question has asked us to make every element of this path equal, so what we can do now? So suppose I decided to change every element of this path to a value which is not present along this path. That is, suppose I decided to change this one to, let's say, 3, and also this to 3, this to 3, and then this to 3. So had I been performing these operations, every edge weight will now become equal to 3 along this path, right? So how many operations does it cost me in order to make this happen? It would have cost me a total of 4 operations, right? Because what I did, I simply picked each one of these and changed it to 3. So that's why 4 operations. If I had chosen 3 and made every initial edge weight equal to this value. But is this feasible? I don't think so. And you might have guessed, because what the question has asked us, it has asked us to minimize the number of operations, right? So we have to minimize the operations, right? So this is like the brute. I am just changing every value to another value. So the total number of operations in that case will be the total number of elements that I am changing. So this is not feasible. What we can have done instead is, instead of changing every value to 3, let's say we decided to change every value equal to 1 now. So if I decide to change every value equal to 1, so what will happen? So now I have changed every value equal to 1, and how many operations does it cost me now? So since this was already 1 and I changed it to 1, it means that I have not changed it at all. So it will not cost me any operation. But for these 2's, I have changed it to 1. Since I have changed it for these 3 2's, so I can say the total number of operations that I have to perform in order to get this is 3 operations. And earlier what we were doing is we were simply changing every element. So earlier we were getting 4 operations, but now we are getting a total of 3 operations. So this is an improvement, isn't it? But the question is now, can we still do a better thing? That is, we still want to reduce the total number of operations, that is less than 3. Is it possible? So suppose now instead of changing every element equal to 1, I decided to change every element equal to rather 2 instead. So if I decide to change it to 2, then what will happen? In order to make this possible, this configuration, I don't have to spend anything for these 3, but for this one, I have to spend a total of 1 cost, that is 1 operation. So that's why for this now I can say the total number of operations that we have performed is just 1 operation. So this 1 operation is just performed for this element in order to change it to 2, and hence now as you can see that we have reduced our answer to 1 operation from 3 operations. I think this is the best that we can do, that is we cannot reduce it any further. And that's why if you see that the output for this query is 1 only, that is 1 number of operations, which is this, and it will take place only when we will be changing this one to 2, right? So that every element becomes equal to 2, and this is what we wanted to happen. Let us now try to answer our last query. This is this. So for this query the nodes are 0 and 6 and the expected output is 3. So here I have marked the nodes, that is 0 and 6, and this is the unique path between these 2 nodes, isn't it? Right? So along this path if you see, then the edge weights present are 1 1 1 and then 2 2 2, right? So these are the edge weights present. Let's see why the output is 3 for this case. So what is our goal? Our goal is to make every element of this path equal. So as I just told you before in the previous query, that if I decide to change every element of this configuration to a value which is not present in this, suppose 10, then in this case I have to perform what number of operations? So since I changed each one of them, that is 6, so I would say 6 operations. But we saw that it is not beneficial to change each and every element, right? Because it is increasing the total number of operations. What better can we do instead is, instead of changing every value to 10, Suppose I decided to change every value equal to this one. So if I change every value equal to 1, then what will happen? So it will be become like 111 and then 111 again. So it means that I have changed these 2's to these 1's now. Since I have changed these 3 2's, so I can say the total number of operations now I have to perform in order to achieve this is just 3 operations. Or what we can have done is, we could have simply changed every element of this path equal to 2. So if I had changed every element equal to 2 now, then these 2 would have remained 2 only, but these 3 ones would have changed now. So they will become 2, 2 and 2 now. And in this case, if you see, then what are the total number of operations we had to perform? So we again have to perform 3 operations, that is for these 3 ones, in order to equate them to 2. So I can say 3 operations again. And that's why out of these 6, 3 and 3, as you can see, the minimum is 3 only. So that's why the output for this query is 3 only, right? So I hope you understood how the outputs are coming for each of the query. What we are trying to do every time instead is, we are just trying to minimize the total number of operations by picking such a value that will decrease the total number of operations, right? And every time we are trying to pick what value, we are trying to pick a value which is already present along this path, right? So we are not trying to pick a value which is not present, because if we try to pick such value and change every value equate to that, then in that case the total number of operations will be the maximum number of operations, and we don't want that. We want the minimum number of operations, and that's why we want to replace each and every value with a value which is already present in this. So it means that we could have equated every value equal to either 1 in this case, either 1 in this case, or 2. And we saw that when we did it with 1, we got 3 operations, and when we did it for 2, we got again 3 operations. So it means that we can either change it to 1 or change it to 2. And since the question has just asked us to give the minimum number of operations, so the weights, final weights doesn't matter whether it is all 2's or whether it is all 1's. So I can say the minimum number of operations is 3 in this case. Let us now discuss the second example. So this is the second example of the question. So for this example, we have a total of 8 nodes, that is from 0 to 7, and we are given 4 queries this time, and the expected outputs are as follows, that is 1, 2, 2 and 3. So let us now try to answer each and every query one by one. So the very first query is this one, that is 4 and 6. So let me mark the nodes now. So this is our first node of the query, and this is the second node, that is 6. So as I told you in the previous example, that in any tree between any 2 nodes, the path between 2 nodes will always be unique. So now if you see, then what are the edge weights present along this path? So these are 6, 6, 4 and 6. What is our goal? Our goal is to make every element along this path equal. So here also, if we decide to change every element to a value which is not existing initially, so suppose I decide to change every value equal to 8 now. So 8, 8, 8, 8. So it will cost me 4 operations, right? And we now know that this is not a beneficial one for us, because we can do it much better. So we should change every element either to 4 or to 6. So we want every element either to be equal to 4 or 6. Otherwise, we will get the maximum number of operations. So if I decide to change every element equal to 4 now, so what will happen? So I decided to change this 6 to 4, this 6 to 4, this will remain as it is, and this 6 to 4. So how many operations does we performed here? So we performed a total of 3 operations in order to change this 6 to 4, this 6 to 4, and then this 6 to 4. So 3 operations. And what was the other possibility? So the other possibility was to change every edge weight equal to 6. So if I change every edge weight equal to 6 now, then how many operations did I have to perform? So I just have to change this 4 equal to this 6. So it means that I just have to do one operation in this case. If you look, then this one operation is the minimum number of operations out of these 3 possible operations. So that's why for this first query, the output is 1. So in the second query, the the nodes are 0 and 4. So if these are our two nodes, then the unique path between them is this one, right? This one. So what are the edge weights coming along this path? So along this path we have 6, we have another 6, we have 4, and we have 8. We will not change it with an element which is not present, because it will give us the maximum number of operations. So let me write the number of operations. So now we are left with 3 possibilities: either change it with 6 or 4 or 8. So if we decide to change every element equal to 6 now, that is 6, 6, 6 and 6. So how many operations we have to perform in this case? So we just have to perform 2 operations, right? Because these two 6 will already remain 6. So we just have to change this 4 and 8 to 6. And what was the another possibility? So the another possibility was to change every element to 4. So for this 4, I don't have to do anything, it will remain as it is. But for this 6 and this 8, I have to perform the operations. So that is 3 operations now, right? And the last possibility was to change every element to 8. Again, if you see, then this will remain as it is, so I don't have to do anything for this. But for these 3, I have to change it to 8. So that means again a total of 3 operations. Out of these 4 possibilities, what is the minimum number of operations that I have to perform? So the minimum is 2 operations, right? And that's why for this query the output is 2 only. Let us now discuss our third query, that is for the nodes 6 and 5. So this is our 6th node and this is our 5th node, right? And the unique path between them is this one, isn't it? And what are the edge weights coming along this path? So they are like 3, 6, 4 and 6. And now if we try to do the same thing, then we know that the maximum number of operations would be 4 only, right? But if we try to change every element to 3 this time, so we can change it all either to 3 or all either to 6 or either to 4, right? So these are the 3 remaining possibilities, and for each one of them, what is the total number of operations? So for this one, I have to change all of these to 3, right? So 3 operations for this case, and to make this possible, I just have to change this and this, right? So 2 operations I would say, and to make this happen, that is 3 operations. And what is the minimum among them? So the minimum is 2 operations only, which is coming when we are changing each and every element equal to 6. So that's why for this query the output is 2. Now let us quickly discuss the last query. So the last query is for the node 7 and 4, that is this node and this node. So the path between them is this, right? And what are the nodes coming along this path, or the edge weights rather? So the edge weights are like 6, 6, 4, 8 and 2. So these are the edge weights coming along this path, and we want to equate them, right? So the possibilities are what? 5 operations, that is the maximum number of operations, or we can change it to either with 6, 4, 8 and 2 this time. So 4 remaining possibilities, right? So if I change it to 6 each and every element, or to 4, or to 8, or to 2. So these 4 are the remaining ones, right? So for each one of them, let's see the number of minimum operations. So for this 6, we only have to change these 3. So I can say just 3 operations for this case. For the 4, I would have to change these 4 elements. So 4 operations for this case. For the 8, I have to change these 4 again. So 4 operations again, and then for this 2, we have to change these 4. So 4 operations again. So what is the minimum out of these? So the minimum is 3 operations only, which is happening when we are changing every element equal to 6. And that's why the output for this query is 3 only, right? So now I think I have explained you both the examples very well. So you understood these 2 examples completely, right? Some of you might have noticed that what we are doing each time. So if you look for this example, what we were doing each time for each query, we knew that we had a lot of possibilities, that is the total number of maximum operations, which we will never want to do. But if any 2 elements are equal at least, then it means that we could have simply replaced all other elements with that element only. So the same thing we did here also. Each element was coming once only except this 6 which was coming 2 times. So we decided to change it with that only, because in that case only we had to change the minimum number of elements and thus got the minimum number of operations also. So it should be very clear to you all by now that for each query what we will do, whatever the elements will be present along the path, we will try to replace or rather find the number of operations for that possibility only after replacing each of the element by that element which has occurred most frequently along this path, because that would only help us to get the minimum number of operations, right? So the element with which we are trying to replace all other elements should be the one which has occurred most frequently, because for that possibility only we don't have to apply the operation on those frequently occurred elements and only have to apply on the elements which are different. So it was a clear observation, right? So this is our best possibility. So now what I am telling you is, or asking you is, how we will find these three number of operations. So what is this 3 equal to? That is 3 operations. So these 3 operations are equal to the number of elements on which we are applying the operation in order to change it to some another value, right? So this 3 corresponds to these 3 elements, because on these 3 elements only we applied the operation in order to change it all equal to the 6 to make every element along this path equal, right? It means that if somehow we are able to calculate these number of elements, that is 3, we will be getting our answer, that is 3 operations for that query, right? What is this number of elements actually equal to? If you see, these number of elements are nothing but the total elements present along the path. So in this case 5, right, minus the frequency of the most occurred element, that is 2 here. So 5 minus 2, 3, which is this. In order to get this 3 now, if we are able to find this quantity and subtract it, then we will get what we want for the query. So what is this 5? If I tell you again, this 5 is nothing but the total number of edges that is present along the path between the two nodes of the given query. Since for this query 4 and 7 was our node, so it had a total of 1, 2, 3, 4 and 5. That is 5 edges. So this 5 represents the total number of edges between AI and BI of a given query. The total number of edges between AI and BI. And what does this 2 represent? So this 2 represent frequency of most occurred element in this path. So since 6 occurred the most number of times, that is 2, because other elements only occurred once, right? So we can say 6 occurred the most number of times, which was 2 times. So that's why 2. And 5 minus 2 equal to 3. That is, we have to change a total of 3 elements. And that's why 3 operations, and hence 3 as the answer for this query. So the thing is clear now. If we are able to somehow answer these 2 things, then we should be able to answer every query for an example. So now the question is how we will actually calculate the total number of edges between the 2 nodes. And later we will see how we will calculate these this term, that is the frequency of most occurred element in this path. So let us now first discuss, because this part is little easier to understand than this one. So that's why I'm telling you this one only first. So now we want to calculate the total number of edges present between A and B. So this was our AI and this was our BI. And we want to calculate the total number of edges between them, that is 1, 2, 3, 4 and 5. So how we will do this? So what we will do now is, in order to calculate the number of edges between the 2 nodes, we won't do it directly. Like, I will not tell you a method in which I will be calculating the number of edges between these 2 nodes directly like this. That is 1, 2, 3, 4 and 5, and we'll be getting our answer. No, I will not tell you this. Instead what I am telling you is, and I think in order to explain you this more better, I should not consider these 2 nodes. So just for a second assume that our AI was this and our BI was this. So now if I asked you to find the total number of edges along the path, that is these, that is 1, 2, 3, that is 3 edges, right? So how will you return me these 3 edges? So if you have studied deeply on trees, even very basic of it, then you would have realized what we'll be doing here. So as I said, we will not be calculating it directly. So what we will do instead is, we will take the help of LCA of these 2 nodes, right? So what is LCA? So LCA is nothing but the lowest common ancestor, right? Lowest common ancestor. And what does this LCA represent? LCA represents the closest point or the closest ancestor between any 2 nodes. So for this example, as I am telling you that consider this as my AI and consider this as my BI now. So if I try to go to their ancestors, so from here I will go here, from here I will go here, and then from here I will go here. So this is the closest to both of these, right? This one is also an ancestor of both this 6 and 7, but this 3 is the closest to them. How this LCA, so let me mark this. So this is our LCA, right? So how will this LCA will help me in order to find the total number of edges present between this 6 and 7 now? So the total number of edges, which is equal to 3 here. So what is this 3 equal to? So if somehow I tell you that I know that what is the total number of edges present from the root of this tree to this node along this path, and also what is the total number of edges present between these two nodes, that is from the root along this path. So if I know this information, then what I will say you now is that this required number of edges between this 6 and 7 will be nothing but the total number of edges present from the root to this node plus the total number of edges present along this path to this node minus whatever we have counted it for these edges, the double of it. From 1 to 6, how many edges are present? So here 2 edges are present. Similarly, how many edges are present from 1 to 7? So 3 are present, minus double of whatever the number of edges are present from 1 to the LCA of this 6 and 7, that is 3. So only one edge is present in this case, so I will say 2 into 1. If you solve this, then what you will get? So 2 plus 3 5, minus 2 into 1 2, so 5 minus 2 is 3, which is equal to this. So that's why calculating LCA proved to be useful in this case, right? If you know how to calculate the total number of edges from the root to any node, that is from 1 to 6 and then 1 to 7 and then 1 to 3, then we can use this information in order to find the total number of edges present along this path in this way that I just told you. And why we are subtracting it twice? Because when we would have calculated the total number of edges from this to this would have come, which we wanted, but this would have also come, so that's why we have to subtract it once. And similarly, when we would have calculated a total number of edges like this, these two would have come, which we wanted, but this would have also come again, so that's why we had to subtract again. So since we had to subtract this edges twice, so that's why we are subtracting it like this. So that's why knowing the LCA for every query is a necessity, right? So I will tell you how we will calculate this LCA using binary lifting, which is another interesting concept of DP on trees. But before that, let us solve this problem of how we will calculate the distance from 1 to 6 and then 1 to 7 and then 1 to 3. Because once we know this, I think it would become very easier for you to calculate this value, right? So let us now try to understand how we will be calculating the distance from the root to every other node. Since I want to calculate the distance for each and every node from the root, so what I will tell you is I will just maintain an array. So let's say name our array as height, because the height of I will represent what? It will represent the total distance, or rather the total number of edges present from the root to this node I. So since in this example we have a total of 8 nodes, so let's give the size for this array as 8. So the indexing is like this, and since we have considered this one as our root, so we will be starting our DFS call from this one every time in order to fill up this height array. So since this is our root, I can say the total number of edges present between this 1 to 1 is 0 only. So for this one, I will say that the total number of edges present from 1 to 1 is 0. From this one, I can go either to 2 or either to 3. So when I go to 2, then what will happen? So the height will increase by 1, or rather the distance, or rather the total number of edges present between this 1 and 2 will increase by 1. So I will say the total number of edges will now become equal to 1 for this 2, and same for this 3. And similarly, if I decide to go from this 2 to 5 or 4, then again the total number of edges along the path will increase by 1. So for 5 and 4 I will say it will be 2. Similarly, if I decided to go from this 3 to 6 or 0, then again the answer would have been 2. So that is 2 for 0 and 6. And at last, if I go from this 0 to 7, then again the total number of edges will increase by 1, that is 3. So if you have noticed, then how we are filling the height array. If we are able to go from a given node to its child, let's say C, so we are just doing one simple thing, that the height of this child is nothing but whatever the total number of edges or the height it took us to reach from the root to the parent, that is node, plus 1. So using this simple relation, I'm able to fill up this height array completely. So we will say that the total number of edges required in order to reach from the root to the child will be equal to nothing but the total number of edges required in order to reach from the root to the parent plus 1, because every time it will increase by plus 1 only. So in this way we will be able to fill up our height array and calculating the distance from the root to each and every node in the given tree. And once we have done this, as I just told you before, that in order to calculate the total number of edges present between the any two nodes, I'll be calculating the total number of edges present from the root to this node plus the total number of edges present from root to this node minus twice the number of nodes or the edges rather present along this path from root to LCA of these two nodes. So I will tell you very soon how we will be calculating the LCA. I should explain you one more thing, that is the frequency of the most occurred element along this path, right? So let me teach you that first, because I think that will also require the use of LCA. And once we are able to understand why, I think after that if I explain you the concept of LCA, then both of those requirements will get solved simultaneously. So let me now explain you the other thing that we required. So now we have to understand how we will be calculating the frequency of the most occurred edge weight along the path between the two nodes of a given query. So consider the original query, that is the last query of this example, between 7 and 4. So this is our path, right? And the edge weights present were 6, 6, 4, 8 and 2. How we will be calculating this maximum frequency? Because once we are able to calculate this, I will simply say the total number of edge weights along this path that we just calculated before using this height array and the concept of LCA. So this 5, that is the total number of edge weights between this AI and BI, minus the frequency of most occurred element, this 2 here. So 5 minus 2 is 3, which will give us our answer. That's why we are focusing now on how we can calculate this too. So if I ask you to look at the constraints of this problem, so if we look at the constraints, then you will see that the value of Wi, that is the edge weight for any two nodes, can go up till 26 only, that is from 1 to 26. So the value of edge weight can be between any value from 1 to 26 only, right? So since the edge weight can be present from 1 to 26 only for between any two nodes, so how we will do this, let's see. So now I am asking you is to actually find the frequency for each and every element from 1 to 26 along this path, right? I don't want you to do this just for 6 or 4 or 8 or 2 or any other value. I just want you to do it for each and every value from 1 to 26 only, because these are the only possible edge weights possible for between any two nodes, as you just saw in the constraint, right? If I am able to find the total number of frequency for each and every edge weight from 1 to 26 along this path, then so let me write that down here. So these are the possible edge weights, right? That is from 1 to 26. And now what I'm asking you is to find the frequency for each one of these edge weights along this path. So if now I start to calculate, then how many times this one has occurred? So it has occurred a total of 0 times. So, and how many times this 2 has occurred? So this has occurred a total of 1 time. So if I do this for each and every edge weight, so let me do that quickly for you. So I have filled the whole thing and this is how it will look like. So as you can see that 6 has occurred a total of 2 times, 4 has occurred 1 time, 8 has occurred 1 time and 2 has occurred 1 time. So somehow if I get this information that what is the number of times, that what is the frequency of each and every edge weight from 1 to 26 between this AI and BI, what is our last job? Our job is just to maximize that frequency, right? So if I start maximizing this continuously one by one, then the maximum value that I will get here is 2, because this is a maximum among all of these. So I will get 2 as the maximum. And once I get 2, I just wanted this to happen, right? Because after that I will just subtract it with the total number of elements, that is 5 minus 2, and will get my required answer, that is 3. So now the obvious question is how we will be calculating these things, right? So again, in order to calculate this, I will just use the concept of LCA only. Let's see how. So let's try to do it for 6 only first and see how this 2 will be calculated. So since now I want to calculate the total number of occurrences of 6 along this path, so as I just said you that we will took the help of LCA, right? So now if you see, then what is our LCA? So for this 4 and 7, this is our LCA, that is 1, which is our root node also, right? So since now I want to calculate the occurrences of 6 along this path, so what does it will be equal to? So it will be equal to the total number of occurrences of 6 along this path plus the total number of occurrences of 6 along this path, that is the two sides of LCA, right? So if I know the total number of occurrences of 6 along this side and on this side, then it means that ultimately I know the total number of occurrences between this AI and BI, that is on both the sides of the LCA. So that's why this LCA would again be useful here. So some of you might have guessed already that what we'll be doing here is, in order to find the total number of occurrences of 6 in this side and then on this side, we will be doing it individually again, right? So in this case, it is a coincidence that this LCA is our root node, but just suppose that there was some another node as well, and that was our root node. Just suppose it to understand more better. So I would have just said that if I know the total number of occurrences of 6 along this path and along this path, then we would have got the total number of occurrences in this path plus the total number of occurrences in this path, right? But we would have also got the total number of occurrences of 6 along this path twice, isn't it? Just to eliminate that, we would have subtracted these occurrences of 6 along this path twice. So that's why I can say, so just as we did for the height array, that we calculated from the root to every other node the height of that node, or rather the distance from the root node, right? So we will do the same thing here also, that is, we will calculate the total number of occurrences for each and every edge weight from 1 to 26 from this root node to each and every node of the tree, right? Because once we know this, then just by using the concept that I just told you, we will be able to find the maximum frequency along this path for each and every element, right? So since now I want to find the frequency of each and every element from 1 to 26 from the root node, so in order to do this, we can just use a 2D DP, that is this, and let's say it as DP of ij. So what does this DP of ij represents? So it will represent the total number of occurrences of edge weight j along the path from root to node I, right? So this DP of ij will represent the total number of occurrences of the edge weight j along the path from the root to the node I. As we saw that the edge weight can go till 26 only, so we will set the size for this as 26 or rather 27, since we want to use it from 1 to 26, right? And what is this I? So this represents the node value. So this represents the node, right? And in the question, if you have noticed, then the total number of nodes can go up till 1e4, right? So that's why we will set the value of this to 1e4 only. So we will maintain this DP state, right? So this DP state, 2D DP state, will help us in finding the total number of occurrences of every edge weight from 1 to 26 from the root to that node, right? So let me do few of that for you so you could understand better. So if I now ask you what is the DP state for this root node, so now what I'm asking you is, what will be the value of this, that is DP of this root and each and every edge weight from 1 to 26, right? So since we are trying to calculate the total number of edges present from this root to the root itself, so for each one of them, if I fill the DP table, then you will realize that each of this value will be equal to 0 only, common sense. And now if I ask you to calculate this DP of the child of root, that is 1 in this case, that is DP of 1 and every value from 1 to 26, then now what it would be equal to? If you have noticed clearly, then it is, and let me also give this edge weight, let's say just assume it, this is not in the actual example, I'm just assuming it so that you can understand it better. So if this edge weight is equal to 7, then what I can say is that the total frequency for each and every element from the root till the root was 0 only, as we just saw. But the same thing, if I ask you for 1, that is the total frequency of each and every element from 1 to 26 from this root till its child, then what would be the difference coming in? So the difference will only be coming in the frequency of this edge weight, that is 7, because when I moved from this parent, that is root, to this child, only the frequency of 7 got increased by 1, and the frequency of each and every edge weight from 1 to 26 excluding 7 will remain 0 only, right? So I can say that the frequency of each and every element from 1 to 26 except 7 will remain 0 only, but for 7 now it will be equal to 1, that is 0 plus 1. So very logical, right? And similarly, if I try to calculate the DP state for this second node and third node, so let me write that down here. So that is DP of this 2, and from each and every value from 1 to 26. Similarly, for this DP of 3, for each and every value from 1 to 26, then you will realize that since we are going from this 1 now to this 2, so the only difference is coming because of this edge weight, right? And again, if I am moving from this 1 to 3, then the only difference is coming because of this edge weight. So whatever the total frequency of each and every edge weight from 1 to 26 is present for this one, it will remain the same for this 2 and this 3 as well, except for this 6 and 4 respectively. Again, I can say that for each and every element from 1 to 26, but except this 6 now, it will remain as it is. So since it was 0 before, so it will remain 0 only, but don't forget that it was 1 for this 7, so just say 1 for the 7, and now since 6 is also getting involved in the path, so 1 for this 6. So I can say it will be 0 for each and every element except 6 and 7, and for now 6 and 7 it will be equal to 1 individually, because from this root node along this path, this 7 and 6 is now coming 1 time, so that's why 1 for them. And similarly, if I do the same thing for this, so I can say that it will be 0 for each and every element from 1 to 26 except this 7 and 4 now. Except this 7 and 4 it will be 0, and for 7 it will be 1, and this for 4 it will also be 1. So in this way we will be filling our DP states continuously. That is, so if I write the DP relation here, so it will be like, if I am moving from a node to a child, let's say C, and the edge weight present between this node to C is, let's say, W, then the DP for this child from 1 to 26 will be equal to nothing but the DP of the parent, that is node, from 1 to 26. So in this way it would have inherited whatever the values the parent node had, right? So it will remain the same for the child node as well, but this W will be contributing now also. So I will say that DP of this child and W will increase by 1. So in this way we will be calculating the DP state for each and every child, right? So now I think I have explained you this in very detail, that how we'll be using the DP states, that is the 2D DP, in order to calculate the maximum frequency from the root to any given element. And once we have done this, that is the total frequency for each and every element from this node, that is root to this node, and similarly from root to this node, I will just be adding the values of these two sides and subtracting the twice whatever has come here, and in this way I will be getting the frequency of each and every edge weight from 1 to 26 along this path, and at last I will just have to maximize those values, right? So after maximizing whatever the value I get, I just have to subtract with the total number of edges present along that path, and in that way I would have got my answer. Okay, so now I think I have explained you almost everything. So the last thing that is remaining us to understand is the concept of binary lifting in order to find LCA. And once I teach you that, I think we'll be good to go with the code. So let us now understand the concept of binary lifting and how it is used to find LCA. And by the way, I want to tell you that there is a dedicated problem for it on CACS problem set also. So this is the problem. So in this problem also we have to find the lowest common ancestor or the boss here for two given nodes A and B, right? This is my solution, and for each and every query that is A and B, I'll be calling this function from the tree class, and this will be helping me in finding the LCA for these two nodes. So the same thing has been done here by using the concept of binary lifting only. And I want to tell you one more thing, that in order to use this thing, that is to find the LCA of these two nodes n1 and n2, you must be knowing how to find the kth parent of a given node. And again, in order to find the kth parent of a given node, there is part 1 of this problem. So in this problem also you have to find the kth parent of a given node only. So if I so this is the solution for it. The same thing has been implemented in this class right here, that is to find the kth parent for a given node, right? So that's why this class supports both of these functionalities together. So that's why before teaching you how to find the LCA for this n1 and n2 by binary lifting, I'll first be teaching you how to find the kth parent for a given node in the tree hierarchy, and after that only I'll be using that concept of kth parent right here in this LCA, and we'll be finding the LCA, right? So then things will become very easy after we learn how to find the kth parent using binary lifting. So for now, consider this is our tree, and in this tree what I want is I want to find the kth parent, let's say for this node, that is the 7th node. So for the 7th node I want to find the kth parent first. So what is the meaning of kth parent, or you can say it as the kth ancestor also, right? Kth ancestor. So what do we mean by it actually is, for this 7, as clearly visible, this 8 is our first parent, or rather the first ancestor, right? Similarly, this 6 is the second ancestor for this 7, and similarly this 4 is the third ancestor for the 7, and similarly this one is the last ancestor, or better say the fourth ancestor for the 7th node, right? So how we will find this, that is the kth ancestor for each and every node? You can do this by two methods. One would be the brute force, that is in this tree hierarchy just go k levels up each time. That is in the tree just go one level up each time till the total number of times you do it becomes equal to k. So if I want to, let's say, go till 3 times, so just go one time like this, and like this. So by doing that you will reach the third ancestor for this 7, right? But let me tell you about one thing, that we can do this in a much better way. That is, if I want to reach from this 7 to this 4, then I don't have to every time go like this. That is one step like this, then this, then this. What I'm saying is that we can do it in a much better way. So we call that trick as binary lifting. So as the name suggests, just see. So binary, that is 0 and 1. So how we'll use this, and what does this technique involve? See, so as I told you that from 7 I want to go to 4, that is k equal to 3, right? That is the third ancestor of this 7 in the tree hierarchy. Now what I'm asking you instead is, can you represent this 3 in binary form? Yes, you can. And what is the binary form for this 3? So the binary form for this 3 is, we know very well that it is equal to something like it would be 0 0 in the initial, and then ultimately it would be 1 1 at the last. So that's why we can say that since this is our 0th bit, first bit, all up to till the 31st bit, right? So that the total number of bits will be 32 for the int. If you are storing this k in int, right? So I can say then that this 1 into 2 to the power 0 plus this 1 into 2 to the power 1, and then it would be 0 for the remaining ones, remaining zeros, right? So if I calculate this, then it would be equal to 1 plus 2, that is 3. So it means that I have successfully represented the given 3, that is this, into a binary form, that is 1 1, right? let me write down the same thing here. So now I have represented this 3 as 1 and 1, and I just explained you by writing here that this 3 can be represented as 1 plus 2. So now if I let me erase this so that you can understand better. So now if I ask you that in order to jump from this 7 3 steps in order to reach 4, the first thing that we saw was a brute force, that is to jump 1 1 1 until we do it for every k levels, right? But now what I'm telling you is, since I want to do it for a total of 3 levels, so instead of doing it for 3, do it for 1 first and then 2 in the second move, right? So first if I do it for 1, that is I jump just 1 level up. So from 7 I will just go 1 level up, or the first ancestor of 7. So by doing that I will reach this 8 only, right? So in this way I would have done this. And again if I tell you that just jump the number of ancestors from this 8 node equal to this value, that is 2 levels up. So from this 8 I will go 2 levels up, and by doing that I will reach this 4 only, right? Because this is the second ancestor for this 8. So in this way I would have jumped from the 7 to the 4, that is the total number of required value of k, that is 3 times, not by using a brute force of 1 2 and 3, but just by using 2 steps now. And by doing those 2 steps only, we reached where we wanted to go. And what actually helped us in doing this is the binary representation of the given 3 or the given value of k. So that's why it is called as binary lifting, because binary suggests that we are just using this 0 and 1 representation in order to lift the node up in this tree hierarchy, right? So that's why binary lifting it is called. So this was a smaller example, that's why it took only 2 steps to reach 4. Instead of doing it for k equal to 3, just assume that I wanted to do it for k equal to 4. So if I wanted to do it for k equal to 4, that is I wanted to go 4th ancestor for this 7, which would be 1 in this case, right? So it is quite up in the tree and I want to go this. So what we can have done is, I could have done a simple brute force, that is first go from 7 to 8, then from 8 to 6, then from 6 to 4, and then from 4 to 1. So this could have been done, but since this was time consuming, so what I'm telling you now instead is just represent this value of k in binary. So what is the binary of 4? So it is 100, right? So this will correspond to the 0th bit, this will correspond to the first bit, and this will correspond to the second bit, right? How can we use this binary representation to get 4? So it would be something like 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2. That is 0 plus 0 plus 4 would be equal to 4 only, right? So now I will just say you the same thing, that instead of jumping one step every time, I will just jump these much number of times, right? Since this is 0, it means that we don't have to jump anything, so I will just not use this. It means that I just have to jump these much number of times now, because 0 will not make any sense, right? By jumping a 0, we will remain where we are at the previous stage. So it means that we just have to jump a step of 4. And by jumping a step of 4 directly, that is this, I can simply reach from 7 to 1. So what does this mean? So it means that if somehow we know for each and every node of the tree what will be the ancestor of that node, if we jump from that node 2 to the power ith number of times, right? This could be equal to either first ancestor or second ancestor or fourth ancestor or eighth ancestor and so on. That is the powers of 2. So if we know this for each and every node, then we can simply jump it in the powers of 2. Because if you have noticed, then what were these values? So these values were nothing but the powers of 2 only, right? So the binary, that's why the binary representation of any number, when you try to combine those values in order to get that number, those individual values will be power of 2 only every time. And if you know what ancestor we will reach for a given node by jumping in powers of 2, then it means that from any given node we can go to any ancestor by jumping in just powers of 2. So the same thing we done here also. Since we wanted to jump k equal to 4 step, and we represented it in terms of binary, and we got just 4, so I just jumped a 4 step from this 7 to this 1. Had it been something like 2 comma 2, that is 2 plus 2, so I would have jumped first 2 steps and then another 2 steps, right? So in this way I am able to reach from the given node to its kth ancestor by jumping in powers of 2, and not merely by jumping one step every time, right? So this is the concept of binary lifting. But now the obvious question is, how we will know that the fourth ancestor of this 7 is 1, right? Or the first ancestor of this 7 is 8 and the second ancestor is 6? Because what I just told you is, I should be knowing the 2 to the power ith ancestor for each and every node in the tree. So if somehow I know the first ancestor for this 7, then I can go it like this. And similarly, if I know the second ancestor for this 7, then I can simply go to it like this. And similarly, if I know the fourth ancestor for 7, then I can simply go it to like this. So that's why I'm now asking you is to just calculate the 2 to the power ith ancestor for each and every node in the tree. And once you know that, just decompose the given value of k into binary and use it in order to jump with those much numbers only, and eventually you will reach where you wanted to go. So in order to do this, we have something called as pre-processing, if you have heard, right? So we will do a pre-processing, and in the pre-processing what we will do is, we will simply store the 2 to the power ith ancestor for each and every node in the tree by using a relation, let's say dp. So dp of a node and this I, let's say j rather. So what does this represent? So this will represent the 2 to the power jth ancestor for this node, right? Let's say this node as I. So node I. So this will represent, this dp state will represent the 2 to the power jth ancestor for this node I. So if we are able to maintain this 2d dp by doing the pre-processing already, then we were able to actually jump in powers of 2 every time in order to get to the kth parent of a given node. So now if I show you up the code that how the pre-processing will be done and how the kth ancestor will be calculated, then I think you will understand it much better. So this was the code, right? So this is the place where the pre-processing will take place. Instead of using dp, I have named it like pow2 ends, right? So it represents the same thing, that for this nth node, the 2 to the power pth ancestor for this nth node will be equal to this. So by running these two for loops, we'll be able to do the pre-processing for each and every node, and thereby storing the 2 to the power pth ancestor in this case for each and every node in the tree, right? And once I have calculated this, that is the pre-processing is done for each and every node in the tree, I want you to calculate the kth parent, right? So what I told you for the kth parent is very simple, that for each and every bit of the binary representation of the given k, we will check which value is equal to 1. So it will check for all the bits. I will be checking the binary representation of the given k each time, and if it is equal to 1, it means that I have to jump that many number of times up in the tree. So in this way I will be updating the current node position equal to the new node position, that is this. So I hope you understood how we will calculate the kth ancestor for a given node, right? And we will use the very same thing in order to calculate the LCA of the tree. So now let's see how we will use this concept in order to find the LCA. So let's say now we want to find LCA in this tree for the nodes 12th node and this 11th node. So now I want to find the LCA for this 12th and 11th node in this tree. What I am now asking you is to maintain a height array So height of this node will represent what? So this will represent the total distance from the root till this node in the tree and nothing much. So for this 12, it will be equal to, that is, height of 12 will be equal to the total distance from the root. So it would be equal to 1, 2, 3, 4 and 5. So it would be equal to 5. And similarly, the height for this 11th node will be equal to what? So it would be equal to 1, 2, 3 and 4, right? So 4. These are the distances for both of these nodes from the root. And now if I take the difference, if we take the difference of the height, then it would be equal to 1, right? So the difference in the height for both of these nodes is equal to 1. So what does it mean? It means that the level difference for both of these nodes is just equal to 1, right? So this 12 is present in one level down as compared to this 11th node. So what now I am asking you is to do is to just bring this 12th node onto the same level as that of 11th. So if I do this, then so this is the height difference between these two nodes. So it means that this 12th node is present at one level more as compared to this 11th node, right? So what now I am asking you to do is very simple, that we have to bring both of these nodes onto the same level, right? So to make this happen, I will say I will jump from my current node position one level up in the tree so that I can be present on the same level as that of the another node. So if I do this, then my current node position will shift from this 12 to one level up in the tree, that is 10. So now my current node position will be this 10. And now if you see, then the level for both of these nodes is equal in the tree from the root, which is equal to 4 only, right? So 4 for both of them now. And let us see how this will help us in order to calculate the LCA. So if you remember, then before this was our original node and this was our original node, and the LCA for both of them was this 4, right? So it means that we want to reach this 4 ultimately anyhow. In the next step, what we do in this technique is very simple, that we start jumping in the highest powers of 2 possible till the lowest powers. By this what I mean is, initially from this 10th node where we are currently standing, since the maximum number of ancestors possible for this node is 4, that is, it can go from this 10 to this 1, right? So I would say I will start jumping from this 10 to the highest power of 2 possible, which is 2 to the power 2 here, that is total of 4 ancestors, and then we will jump 2 to the power 1 and then 2 to the power 0. Similarly for the 11th node we will do the same thing. Since for this 11th node also the highest we can go up in the tree is 4th, so 2 to the power 2, 2 to the power 1 and 2 to the power 0. So for both of these nodes we will simultaneously jump 2 to the power 2 for both initially, and then after 2 to the power 1 and then 2 to the power 0. And let's see what happens if we do this. So if we do this, then let's jump from 10 2 to the power 2. So by doing this we will reach here, right? And at the same time if we jump from 11, then we will reach here. And as you can see right now, wherever we reached, these are equal in value. So for 10 we reached 1 and for 11th also we reached 1. Now I want you to jump for 2 to the power 1, right? So let me erase this now. So if I jump 2 to the power 1 from both this 10 and 11, then where should I go? I should go 2 to the power 1th ancestor for both of them, that is second ancestor. So from this 10 I will reach this 4, and from this 11th I will again reach this 4 only. So by doing this, again if you see, then we have reached a place such that the 2 to the power 1th ancestor is same for both 10 and 11. So this might be our LCA, but we are not sure. Why? Because the same thing was coming in just the previous step when we jumped 4 steps. So that could have also been our LCA, but we know that that was not our LCA. But how will the computer will differentiate in these two things? That is, this would not be our LCA, but this would be our LCA. So the computer will not. Instead, what it will do is, as I just said, it will continue exploring the rest possibilities, right? So if I continue doing this, let me erase this. So just see what happens. So now if I jump 2 to the power 0th ancestor for both of these nodes, that is the first ancestor. So where I will reach? I will eventually reach from 10 to 8, and then I will reach from 11 to 9th. So now I am standing at 8 and at 9th. And now if you see, then what has happened? Now my 8 is not equal to 9. But before doing this, what has happened for these two cases? Instead is, my 1 was equal to 1 and my 4 was equal to 4. So that's why we knew that since the values were coming equal, so we were not sure that if that was my LCA or not. But now since my values are not equal, so I will stop at this point. So if there were some other powers of 2 remaining, suppose for another example, then we will not go to that part. We will simply stop at this point. And now if you look very carefully, since we are standing at 8 and 9, so let me mark that only. So we are standing at 8 and 9th now, and whatever the immediate parent, that is up of this 8 0, this will be exactly same as that of up of 9 0. That is 2 to the power 0th ancestor, which is the first ancestor, which is equal to the immediate parent for both 8 and 9. These two will be equal, and it will eventually be equal to only the LCA only, right? So that's why once we reach this condition, we will simply return this, which would be equal to LCA only. So you can return any one of them, and that would be our LCA. So I hope you understood this technique of binary lifting, that how we initially understood the pre-processing stage and how we utilized that pre-processing in order to find the kth ancestor for any node, right? So same thing we did here also. Initially we calculated the height difference, and whatever the height difference came, whatever the node was present deep down in the tree as compared to the other node, we simply made that node lift up in the tree by that much number of ancestors, right? And once we did that, what I told you is to start jumping from the highest powers of 2 till the lowest powers. So it jumped first till 1th and then 4th, but it was not sure that which one of them was LCA. So it continued doing that until the nodes that we were reaching were not equal. So it means that we have reached a level which was just below the LCA level, right? So we just returned the parent of where we were standing, and that was our LCA. And the same thing I have done here also, if you see. So I am just comparing the depth of the two nodes, and in our example also, the whatever the node was present on the left side was our N1, and on the right side was our N2. So the same thing was here also done. So if this is not the case, that is if the case was opposite, so I will just call the same function with opposite parameters. And after that, what I did was I just jumped the difference of both of these levels in order to make both N1 and N2 reach the same level. And if after jumping they both become equal to the same level, this will only be possible when out of these N1 or N2 either will be our LCA. So if the LCA of both N1 and N2 is either N1 or N2, then this thing will be true. And if it is not, that I just told you that start jumping in powers of 2 from the highest to the lowest, right? And in process of doing this, if at any time we encounter that the 2 to the power ith parent is not equal, then it means that we have reached a level just below the LCA. So at this point we will stop. Simply I can have added my break statement also here, because I don't need to go any further now. And at last just return this, that is the immediate parent from where I am standing, and this would be my actual LCA. So I hope you really understood each and everything that I explained in this video till now, that how we'll be solving this problem. So let me summarize everything up so then coding will become very simpler for us. So what I explained you is mainly few things. So the first thing was how we calculating the height for each and every node from the root, and the second thing was how we will be calculating the total number of occurrences of each and every edge weight from 1 to 26 from the root to a given node, right? So I explained you that, and after that I explained you that in order to calculate these two things we'll be requiring the LCA, right? And in order to understand LCA, I explained you the kth Manchester and the pre-processing concept. So by using this kth Manchester and pre-processing, I estimated my LCA, right? And once LCA has been calculated, I will simply use it in order to calculate the total number of edges present between and the maximum frequency of an edge weight. So now I think I should start writing the code in the Leetcode code editor. So, and after that everything will become so clear to you. And if you are still watching the video and have not liked the video yet, please do consider liking and subscribing the channel. And because it takes a lot of efforts to create each and every single video, as you can see that I really tried my best to explain you each and everything in very detail, right? From the actual examples to the concepts involved, like this. So please do consider liking, subscribing and sharing the video with others. So now let's get back to the code editor and write the code. So this was our question, right? And as I just told you in the CSS problem statement that I'll be using the same template of tree here also. So I have copied that. So this is the template for the tree, and this will give me the kth parent and the LCA for the two nodes. So let me start writing the actual code in this class. So what we'll be doing initially, I will be constructing an adjacency list based on this edges 2D vector, and I will use that adjacency list in order to build my height array and use it in the DFS function, right? So I will be iterating through these given edges. It will consist of three things. So each of these vector consists of three integers, that is u, v and w. So after I have write this, so I will say that g of u dot pushback. So in this way I have constructed an adjacency list bidirectionally. So let me declare this adjacency list here. I will just declare it globally like this, right? And after this has been done, what I will do is, and moreover I will be using this particular adjacency list, that is G, in order to build the tree, that is for this template, right? And in order to calculate the heights and other parameters like the DP state, I'll be using another adjacency list. So I will be storing both the node as well as the edge weight this time also. So I will say G. After this has been constructed, what I will do now is I will initialize this tree as this, and the parameters that I have to pass here is as I said, I will pass this adjacency list G and the total number of vertices present in the tree, which is equal to n, right? Now what I will do is I will call my DFS function from the root node, and I will say that initially its parent would be -1. So void of DFS int current node and its parent p. And if you know how to do a DFS on a tree, then in this we don't use any visited array, we just use the parent, right? So I will say for each child of this node, if this child is not equal to the parent, it means that we can go in the tree, right? And instead of this node, it will not be node, it will be instead dw of this node. My edge weight will be equal to c dot second, right? And since this is a pair, I think instead of writing it as int, I should write it as pair only, right? And in this way my adjacency list will be storing both the adjacent node and the weight in order to go to that node. So if my child is not equal to this parent, it means that we can continue our DFS in the tree. So I will just say that the height of this child will be equal to the height of this node plus 1. So let me declare this height array also here. So in this way my height array will be filled for each and every node in the tree, right? And I just have to call the dfs function again, but for this time I'll call it for child and its parent would be this node. And if you remember, then we used to do one more thing. For each child node, we clone each and every value from its parent node and add one more value along the weight, right? So I will do the same thing here also. So I will say that the dp of this child for each and every value from 1 to 26, let's say as j, would be equal to the dp of its parent. So what is the parent of child? It is node only, right? So node of j. And after that, just say that dp of this child and this weight, that is wt, increase it by 1, as I just explained in the explanation very well. And since this is happening for all values from 1 to 26, so just run a loop from 1 to 26. So j from 1 till 26. So in this way we will be cloning each and every value from the parent dp state to the current child dp state and adding one more in order to fill up this dp table. So let me declare this dp table here also. So in this way my height array and dp states will be filled, and after this has been done, I will simply iterate through the given queries. And as I told you in the explanation that for both of these ai and bi, I will be calculating their LCA each time. So let's say LCA of ai and bi will be equal to what? So it would be equal to nothing but tree.lca ai and bi. So by doing this I will get the LCA for both ai and bi in the tree. And once I have this, what I told you in the explanation, I told you that we will be calculating the total number of edges present between ai and bi in the tree. And I also explained you how we will do this. So I will say total edges between ai and bi, it will be equal to nothing but the height of this ai plus height of this bi minus 2 times the height of their LCA, that is this. So the first thing is done. And what is the second thing we want? We want the maximum frequency for each and every element from 1 to 26, right? So I will say initially that my max is 0 and I want to maximize the frequency, right? So we will iterate for each and every possible element from 1 to 26. So now I will be trying to calculate the frequency. So I will say that the frequency will be equal to nothing but dp of this ai and this jth node plus the dp of this bi. So what does these two things represent? It represents the total number of occurrences from the root to the ai node for this j, and similarly the total number of occurrences for this j from the root to the bi node. So these two things minus 2 times the dp of LCA of ai and bi. So let me copy this, that is this. So in this way I will be getting the frequency for this j value between ai and bi. And since I just have to maximize this only, so I will say max equal to max of maxi comma this frequency. And after this loop will be completed, I will get the maximum frequency. I will get the maximum frequency of some element, and whatever that frequency would be, since I wanted to answer the minimum number of operations, so I will say result. So I'll be storing the answer in a result vector, since I have to return a vector only. So I will say the total number of edges present between ai and bi minus whatever the maxi value is, that is the maximum occurring frequency. So in this way I'll be storing the minimum number of operations for each query, and at last I just have to return this result vector. So now I think I have written the complete code, and now if I try to run up the code, let's see if this is working fine or not. So as you can see that both the given examples are giving correct answer. So now if I try to submit the problem, let's see. So as you can see that our solution is accepted now. So in this way we solved this Leetcode hard problem. I know this video has got a little lengthy, but it was worth it, right? Please consider liking this video and sharing the channel with your friends, and if you have not subscribed yet, please subscribe the channel also. because it takes a lot of efforts to create each and every single video, right? And I have planned to upload more and more videos related to the harder problems on Leetcode, codeforces, CSES and other platforms. And if you have any suggestions regarding anything, please write down in the comments. I will read those comments and will try to act on it. So yeah, thank you for watching this video. Thank you.